The molecules. We got to cyclize them. We're going to make them into a ring in a minute. Okay, now let's get familiar with these. Fisher projections, because what we've got this one on the right. Well, for D-glucose. I mean, this is a chiral carbon. This one is one, but that's a chiral carbon. Chiral carbon, chiral carbon. So in the Fisher projection of D-glucose, you're going to have an OH on the right, left, right, going up from the bottom. So you got right, left, right. That's D-glucose. I mean, there's L-glucose, but we are going to very quickly here. We're going to be talking about only D. Because D is the biologically active monosaccharide. That's why we're spending all this time on this. The trees out there are making D-glucose exclusively. Not a mixture of these two monosaccharides, but 100% D-glucose. All right?
So what would it be if all the OHs were on the right?
I've got a slide that will answer that in a few minutes. And on that slide, I'm getting my cord here. On that slide, it's going to show you 4 or 5 monosaccharides that I want you to memorize the positions of these OHs. Of course, and I don't think it would surprise you that D-glucose is one of them. Okay? So you need to know it's right, left, right. And that's the Fisher projection of D-glucose. It says my battery is on saver mode. All right. This kind of goes through telling you how to do these Fisher projections. All right, let's go over this slide. Is it D or L? And we're going to so right here we have, that's 3 carbons. What's the name of that molecule? Aaron? Glyceraldehyde. And which glyceraldehyde is it? D. Okay. D. D. I only look with questions in my eyes to challenge them, to see how confident you are in your answer, you see? So there, you're right. D-glyceraldehyde. So we're going to look at that carbon right there and say, is it on the right? D. If it's on the left, it's L. So that molecule up there, is it D or L? Yeah, that's a ketose. So focus on that carbon. Where's the OH? And it is D. D. L. Okay, don't get mucked up in all this stuff. Just look at this. 1 carbon from the bottom. 1 up from the bottom. So this is an L. This is D. This is D-glyceraldehyde. This is D. This one. L. And this one. D. At least it's the start of a D. At least for that carbon. Focusing on that carbon. The OH on the right is D. OH on the left is L. Okay, now D and L chemically are pretty similar. If we made it in the lab, it would end up being a mixture of D and L. Probably 50-50 mixture, D and L. It would be randomly forming. But the glucose that's being produced in the green leaves outside is not randomly forming. The living system is very specifically making D. It's doing that through proteins and some really sophisticated chemistry. But chemically, they are very, very similar. The only way we could go in the lab and figure out the difference between D and L would be by which direction it rotated polarized light. A polarimeter. You could use a polarimeter to distinguish whether you have the D or the L isomer of a monosaccharide. So you take a light bulb with just monochromatic light, put it through a Polaroid filter, and it will block all of the, not the wavelengths, but the orientation of that light, which way it's vibrating. It will block it all out except one orientation coming through. And if that light passes through your sample, D will rotate that polarized light in one direction, and L will rotate it in the other direction, and the polarimeter can pick that up and tell you what it is. But that is it. That's not a chemical effect, that's a physical effect, how it is interacting with polarized light. All right, there are only a few examples of L monosaccharides in nature, in living systems. L lactic acid, D lactic acid. D glucose is sweet. L glucose does not stimulate the taste buds. It's not sweet. Very subtle difference there, but it doesn't fit into the protein that detects sweetness the way the D fits in there. So it doesn't taste sweet, and it doesn't metabolize. Because it won't be received into a certain pocket of a protein, it won't even be metabolized. When we get to amino acids, you're going to find that the amino acids are L. When we do get to the amino acids, you're going to find us coming back to these two molecules. D and L glyceraldehyde are going to be our reference molecules for deciding even amino acids, whether they're D or L. So we'll come back to these molecules. I'm going to toss these on my desk and make sure I don't rip them apart. So when we get to proteins, we can use those. All right, so let's just get a little bit familiar with carbon numbering. All right, what the distinguishing carbon on glucose is the one with the carbon-oxygen double bond, the aldehyde functionality. So that's where we are going to start counting the carbons. That's carbon number 1. You can see there are 5 more carbons, and they each have an OH. So there's nothing, the carbonyl is the more distinguishing functional group on this molecule. We're going to always draw it at the top, and we are also going to start counting carbons from there. 1, 2, 3, 4, 5, and 6. And notice, right, left, right. There is the Fisher projection of D-glucose. All right, that's the Fisher projection. So if your homework says, or a test says, draw the Fisher projection of D-glucose, those OHs, those 4 OHs need to be in that orientation. Right, left, right. Yes?
If we start from the top, then why do we start saying right, left, right? Why don't we
From the bottom?
I mean, from the bottom, yeah. Why don't we go right, left, right? If the double bond's at the top, like why don't we just go down?
Well,
Could you figure out what the chiral is, maybe? Is that what you start counting from there?
well, it's just the way I say it. I mean, you could say it that way. Maybe I should stop saying it, but I mean, learn it however you want to. Probably why have I done that? Because this is the comparable carbon on diglyceraldehyde. This one. So I'm always, even though that's carbon number 5 in glucose, it's the chiral carbon in glyceraldehyde. So I'd have to watch some YouTube videos to see what other people say, to be honest, really honest about it. Learn it however you want to learn it. Photographic memory, whatever you want to do, but they need to be that way. I mean, it could be right, left, right, right. I don't know. You got to learn it one way. Pick a way. I know by habit, I start at the bottom and will go up. So, well, okay. Keep that one in mind. That one's not on the future slide here. There's D-glucose again, where they are, and here is our reference molecule. And you see, so that's on the right. That is comparable to this carbon right here. That's why I start there. Okay, now this is an important slide. Very important slide, because I'm going to show you on this slide the 4 of these that I want you to memorize. I want you to memorize their structures. And a couple of them you can guess. This one, that is our reference molecule for whether something is D or L, D-glyceraldehyde. What do we have on this slide? You can see they're all D. They're all D. So we're looking at, so here's 3 carbon aldoses or aldotrioses. There is only one D-aldotriose, D-glyceraldehyde. There is an isomer of it, but that's L-glyceraldehyde. We don't have any L's on this slide. Follow me? This is just nothing but D. So when there's only 3 carbons, there's only one D-glyceraldehyde. That's its name. Here's the aldotetroses. D-erythrose, they're both on the right. D-threose, right, left, going from the bottom. Sorry about that. It's my habit. All right? Right, left. You can see there would be 2 L's, but we don't have them here. Those are the 2 possibilities.
We only need to know the top ones?
No.
Yeah.
You don't need to know any of those.
Sweet.
Okay, D-ribose. Now the next 4 here have 5 carbons in them. Aldopentoses. There's D-ribose. Right, right, right. They're all on the right. Now why would I want you to pay attention to D-ribose as a monosaccharide? What's so important about ribose as this? It's in, you're close. It's not in DNA. It's in RNA. That's what the R stands for. Ribonucleic acids. So the R in RNA is named after this monosaccharide. So what we'll learn in chapter 20 is DNA and RNA has a sugar phosphate backbone. Sugar. What sugar? RNA, ribose. That's the sugar in RNA. So I'd like you to know that sugar. And then there's D-arabinose, D-xylose, D-lyxose. All right, there's other pentoses, but don't worry about those. Okay, now you get up to 6 carbons. Look at 6 carbons. All of these have 6 carbons in them. So D-glucose is not your only 6-carbon monosaccharide. but it is certainly one that you should memorize the Fisher projection of it. And the other one is D-galactose. The sugar in milk is lactose, and it is made up of these two monosaccharides, glucose and galactose. All right, so those are the four. And then the other one you would want to add to this is fructose. It's not on this slide because fructose is not an aldose. It's a ketose.
So we don't need to know ribose or xylose?
No. No.
And none of the 4 carbons?
No, none of those. Now you tell me why threose is named threose when it has, why isn't it named fourose? That's a joke.
I thought it was, actually. I was going to know.
Okay, thank you. Thank you. Thank you.
Is he being...
All right, all right. All right. I just don't want you to miss anything. So fructose has so this is fructose. Oh, this has got a CH2. Just keep in mind that fructose has a CH2OH at the top and the bottom. This is still carbon number 1 up here. All right? And then the carbonyl is carbon number 2. And then you have those 3 chiral carbons, and then you end up with the CH2OH, fructose. So you should know that structure also. So 5 monosaccharides that I want you to be able to draw whenever necessary.
So just ribose, glucose and galactose, right? That's it?
Right.
None of this, okay. Check.
Okay, can I move on?
Yes.
Okay, fructose is a bit sweeter than glucose, so gram for gram or milligram for milligram, fructose is going to seem sweeter than glucose. So grapes, I mean, a lot of times you eat grapes and you think, boy, those are really sweet. But grapes have a lot of fructose in them. They're high in sugar, generally, but the sugar that they do have is also stimulates the taste buds. These things are solids at room temperature. Your sugar bowl, just look in your sugar bowl. No water, it's crystal, white crystals. That's what all of these things are. And they're highly soluble in water because of all the OHs that are on them. Okay, now we're going to do the next step with your molecule, the ring structure. So we've been looking at these molecules as just the open chain for right now. Before we look at the way this chain closes into a ring, I just want to remind you of the hemiacetal reaction. Okay, now remember the hemiacetal reaction. It's the reaction of a carbonyl with a COH or alcohol. Gives you a hemiacetal. So if we came along here with an alcohol, let's just, in what we did this in chapter 13, so this shouldn't come to you as a surprise or something you never heard of before. This is the hemiacetal reaction. We're adding an OH across a carbon-oxygen double bond. And what happens? We're adding something across a double bond. When you do that, when add it, one part of it goes on one of the things. So the oxygen is going to go on the carbon. The hydrogen is going to go on the oxygen. And what are you going to get? Well, if the hydrogen goes on the oxygen, you're going to get an OH up there. Here's the other part of this molecule. All right, I'm just drawing it the same way I had it over there. And the oxygen of the alcohol and the whole rest of the alcohol molecule is going to be attached to the carbon. There's your hemiacetal.
Is there still an H on that second C or no? Under the OH?
Oh, yes. Thank you. Yes. Okay? All right. So what do we have? We have a carbonyl reacting with a COH. Now, let me see someone's molecule. So we got a carbonyl. Here's glucose. So on this one molecule, we have a carbonyl and we have OHs. So it can accomplish this hemiacetal reaction with itself. Okay? Doesn't have to react with another alcohol. It's got alcohol right here. All right, now, which alcohol? This very first one is too close. You think, well, isn't that great? Well, to actually get this to get in here somehow is going to make too small of a ring. So this one is too close. This one's starting to come along. This one is very real possibility. But this one, which carbon is that? 5. Carbon number 5. The OH that's on carbon number 5. Now watch, I'm going to wiggle this around a little bit. Wiggle this around. And what do I end up with? I end up with an OH sitting right next to the carbonyl. See that? And what's going to happen? This H is going to go on to the O. This O is going to go on to the carbon. We're going to form a carbon-oxygen-carbon bond. All right, so get that far. Get your glucose. Find carbon number 5. And I'm going to cyclize this. Matthew, you want to help me? Stand here, face the class, and hang on to that carbon and that carbon. Okay. Okay, now watch me here. We're going to break this bond. And I'm going to take the hydrogen off of there and put it on that bond. And what have I done? I've formed an OH group. And what am I going to do? I'm going to switch this oxygen around here and bind it right to that carbon. And I've got a carbon-oxygen-carbon bond. And an OH. Where's that OH? That OH is the oxygen that used to be the carbon-oxygen double bond. Is now an OH. You follow me? All right, thanks, Matthew. All right, so do that. And what do you end up with? Now, what you should end up with is 5 carbons and an oxygen in a 6-membered ring. 5 carbons and an oxygen. And this carbon is carbon number 1. And this carbon that has this CH2 group attached to it is carbon number 5. You can keep track of which carbon is which. And you got a 6-membered ring with an oxygen in it.
Can you go back to where it was lined and then just tell me which oxygen and hydrogen is?
It was carbon
again?
5.
I missed that part.
Yeah. Okay, now here's what it looks like. All right, so you got the carbonyl. You got the carbonyl on carbon number 1. And you got an OH on carbon number 5. That's what's getting involved right now.
So I've got that.
Okay, so now break this bond. Break the double bond. Don't take it off, just break it.
Okay.
Leave it on the oxygen, and now move the hydrogen over to it.
That hydrogen.
That hydrogen.
Okay.
Just take the hydrogen off.
Just take the hydrogen.
Not the bond, just the hydrogen, and put it on there. And then that leaves that bond right there to bond to the carbon. Okay?
Why doesn't it just connect to the last one? That seems more logical to me.
That's a good question. Somehow 6-membered rings are, that, if it did the last one, it'd make a 7-membered ring. And 6-membered rings are cyclohexane, benzene. I don't know. 6-membered rings seem to be favored for some reason or another. But this is what it does. It doesn't do some 5 and some 6. It does 5. 5, 5, 5, 5, 5.
That would make it like sigma Steven.
Yeah, that's why I like it better than.
Yeah. I don't know. There's probably someone who's why 6-membered ring would be favored by nature. I don't know.
This is one.
That's what you end up with this way. Now, if
also right
Virgil
here, right?
says this, it ends up with a 5-member.
That's
So it doesn't have to be a 6-member.
1, 2, 3, 4,
You'll
5,
see it
6.
come up on the slide. It's a 5-member ring. Okay. All right, let's get back to, there's more we got to do here, because now we got to learn how to draw your molecule and figure out which molecule you have there. There's some options. Now, how to draw it. Notice this one. This one, let's see, let's make this bigger. Ah, beautiful. See, there's carbon 1, 2, 3, 4. There's carbon number 5, and this is carbon number 6. Okay, now I'm going to show you how to draw this. And you can see the CH2OH group, that carbon number 6, is above this ring. Now here's the way I like to think about it. I like to think about this, it's like a trampoline. Okay, now follow me. Here is, I'm going to draw a 6-membered ring like that. The O is going to be up in the top right-hand corner. Now imagine, sometimes you'll see them, they'll draw this out here so it looks like this is projecting out towards you. They'll color it in. So to give the impression that ring is horizontal. You're looking at the ring horizontally. Now where do I get the trampoline? Well, a trampoline needs some legs on it. Is that starting to look like a trampoline? And if you're a safety-minded parent, you have a screen around it. So there's the rods to go up for a screen. The CH2 is above the trampoline. For D-glucose, there's going to be an OH down here below. There's going to be an OH here above and an OH down here. This is D-glucose. Okay, what about carbon number 1? Carbon number 1 has an OH group on it. Now what you need to figure out is whether you made alpha D-glucose or beta D-glucose. With it drawn like this, let me see, depending upon where this carbonyl was, where it was oriented, when this OH added across here, this is carbon number 1. So when this hydrogen came onto here and this oxygen came onto that carbon, depending upon how that aldehyde was oriented, you could either get the OH ending above the ring or below the ring. And above the ring is beta D-glucose and below the ring is alpha. Now the way you have to look at it keep in mind, the way you have to look at this is with this orientation. The CH2OH has to be above. So, and the oxygen has to be, let me see yours. Okay, so what am I going to do here? I'm going to get this 6-membered ring and I'm going to drop it into this configuration. I'm looking at the trampoline here with the oxygen here and the CH2OH above the trampoline. Where is this OH? It's pointing down, right? So it is alpha. If the OH is down, it's alpha D-glucose. And if the OH is pointing up here, it's beta D-glucose. Now don't change yours. Both of those are naturally occurring. There is one disaccharide that is half alpha D-glucose and the other half is beta D-glucose. Bound together forms a disaccharide. So nature will use both alpha and beta. So don't think that, oh, I got to switch it from alpha or beta. Both of them are biologically active forms of the ring structure of glucose.
What's the OH in the middle?
Which this one? Oh, it's not connected there. It's connected here. Okay, that's a little funny there.
And there's an OH.
All right, is that better? No, there's not an OH missing. Oh, what happened? Where'd it go? There isn't an OH missing. You'd say, well, there might be one missing there. Well, that OH that was on carbon number 5 formed that carbon-oxygen-carbon bond right there.
No, but the first carbon, isn't there missing an OH?
Oh, yeah. So if there is an OH here, this would be beta D-glucose.
So if there was an OH there, right?
Yeah, and if there is an OH, if there's an OH down here, it's alpha. Down here is alpha D glucose. Okay? So those are the two forms. And so, I mean, ordinarily when I would draw it, I wouldn't necessarily have to blacken all that in, but you always got to have your oxygen up here. You always have to have your CH2OH up here. And so with that arrangement, then you start talking about where are these OHs? Below, below, above, below. And that is alpha D glucose. So it's only when you get in, and these are Haworth projections, and it's only with the Haworth projections that you start seeing alpha or beta. Alpha or beta, depending upon where that OH is on carbon number 1. All right, there is a slide of it. Beta above, alpha below. There's just another representation of it right there. Oh, there we go. There's how you spell cyclization. We got there. Cyclization. Whoa. It's not a word I use that often. Here's just an example where you ignore the hydrogens. All you do is just show where the OHs are. You don't have to draw in the hydrogens. Better not to draw in the hydrogens because it just gets too busy. We just kind of want to know where the OHs are, and we assume the other position is a hydrogen. Just to point out that fructose will form this 5-membered ring. And you got a CH2OH above here. Again, you could have a CH2OH above here on the other end of it. And if the OH is below, it's alpha. And if that OH is above, it's beta. Still sticks with that, alpha and beta. And so that is giving you, this is fructose, would give you the furan ring. Glucose would give you the pyran ring. All right, a reaction that we talked about in chapter 13 when we talked about aldehydes. We said that glucose can be oxidized to gluconic acid, and a way you can do this in the lab would be to use copper or the Benedict's reagent, which is blue. You can use Benedict's reagent to oxidize glucose to gluconic acid, and this is the Benedict's reagent is blue and it turns red. All right, so that's your Benedict's reagent, Benedict's test for a reducing aldehyde or a reducing sugar. So even glyceraldehyde, boy, oh man, that's beautiful. We should use that in the lab. We should try that in the lab. I don't know if we have glyceraldehyde. Probably do. But that would be another one that would give us a positive Benedict's test. But what is kind of interesting is that fructose is not an aldehyde, but it is a reducing sugar. How does that happen? Fructose can go through a rearrangement. This carbonyl can wiggle its way up to an aldehyde. It can kind of go through this transition, an ene-diol transition, to become D-glucose. So if you do a Benedict's test on fructose, you might predict that you would get a negative test because it's not an aldehyde, when in fact you will get a positive test. We will do that. Those of you in 1107, we'll do some more Benedict's tests on a whole bunch of sugars, fructose being one of them. But don't get too caught up in this. It's just the explanation for why fructose can give a positive Benedict's test. All right, this slide started introducing you to the fact that glucose does a whole lot more in the body than just provide energy. It can be, well, actually this is an important little intermediate. Glucose will transport into the cells of your body as glucose. The very first thing the cell does when that glucose is transported into the cell, it's kind of stingy. The cell likes glucose, so whenever glucose comes in, it puts a phosphate group on it, so it can't go out. It sticks it in there. It makes it so it sticks in the cell, stays in there. So the very first thing it will do, the cells of your body will convert glucose into beta-D-glucose 6-phosphate. Puts this phosphate group on it. It's big, it's charged, and it no longer can get across the cell membrane. So it's in there. So, and the cell needs it for energy, and it sees the glucose coming along. You know, it's like you. Someone offers you a Snickers bar, and you're not hungry. But what do? Put it in your purse. And you say, those of you that have a purse, and you say, I'll eat this later. That's what the cell does. The glucose comes in and goes, I'll eat this later. But how does it save it? Wraps it up in a phosphate. Glucosamine, all right? See, this is your organic chemistry is coming back to you. Glucosamine. Take one of the OHs off of there, a particular one, and put an amine group on it. You got glucosamine. All right, so this is just an example of how the body is doing more than just burning the glucose. It's using it for other things. People buy this. I know people buy this supplement to help their joints that take glucosamine. I don't know if someone wants to do an extra, if someone wants to do their project on glucosamine, you could do that. Does that work? Why are we selling glucosamine? Is it effective? Does it have any side effects? Does it have to be a particular glucosamine? Does it have to be a certain, which supplements would have a mixture of D-glucosamine and L-glucosamine, and half of it isn't even useful because half of it is L-glucosamine. I don't know if that happens. I don't know. I don't know that much about this molecule. That's why we have these projects. Okay. All right. Right. What happened? Ugh. This thing is too touchy. Here's ribose. Deoxyribose. All right, we already said ribose is the sugar you're going to find in RNA. Deoxyribose, DNA, is not standing for this D, it's relating to this D. And notice what you've done here on that carbon there, carbon number 2, you've stripped off an oxygen. That is a very unusual monosaccharide. And it makes up the sugar phosphate backbone of your DNA molecules. It has a very unusual sugar in the sugar phosphate backbone. It has stripped off one of the oxygens. There's nothing random going on about the stuff that goes on inside your body. It's not random. It's very incredible chemistry, actually. All right, there's fructose again. I'm not going to dwell on it. Glucose, beta-D glucose, below, above, below. Beta-D galactose, below, above, above. So very, very similar molecules. Just the position of one hydroxyl, and it's on carbon number 4. 1, 2, 3, 4. Carbon number 4 is the position that distinguishes glucose from galactose. And there's also beta-galactosamine. Okay, disaccharides. Disaccharides, 2 monosaccharides chemically linked together with a glycosidic bond. I thought I had that word on here somewhere. And what you're getting is, so here is one disaccharide, maltose, and maltose is alpha D glucose and beta D glucose. So I'm saying that they're both biologically active. You take those 2 Haworth projections of D glucose, bind them together here. You got a carbon oxygen carbon bond. So this is an ether linkage right here. It's carbon number 1. Here's carbon number 1 right here. Carbon number 1 and carbon number 4. So this would be a 1,4 link between those 2 monosaccharides, and you're getting this bond between them. So you've got your one monosaccharide over here, the other monosaccharide over there. They're just drawing this down here just to kind of link it together. And you're splitting out a water molecule. Split out a water molecule, you form a disaccharide. This is a glycosidic linkage here. It's a 1,4 glycosidic linkage. And you got the disaccharide maltose. Sucrose, common table sugar. Sucrose, glucose, and fructose. And so glucose, you got your 6-membered ring there. Fructose, your 5-membered ring. You bring these two together. This would be alpha D glucose and beta D fructose. Everything's D from now on. And you would form sucrose. All right, remember I told you the OSE tells you we're talking about carbohydrates or saccharides, but it doesn't tell you whether it's mono or di. Fructose is a monosaccharide. Sucrose is a disaccharide. And then lactose. You've got galactose and glucose bonded together. Again, a carbon-oxygen-carbon bond. Carbon-oxygen-carbon bond forming lactose. Something about galactosemia and lactose intolerance. What slide are we on here? 42. Let me, I'll get polysaccharides in on Wednesday, but let me just go to this. We're talking monosaccharides and some ways they pop up in your body. How do the saccharides? Well, blood type. Blood type is geared off of saccharides attached to hemoglobin. So here is, let's make this a little bigger. So here's the key. So these yellow rings right here are the cyclized form of galactose and some other monosaccharides that we haven't, sialac, fucose, acetylgalactosamine. So there's other monosaccharides being represented in here. But basically just a little, this would be an oligomer. Remember an oligomer? Not 2, not 1,000, but 3 to 10. So here's a little oligomer, 1, 2, 3, 4, 5 monosaccharides bound together. On the side is the signal for what blood type this is. Okay, this is what's going to set the alarms off if you get the wrong blood type. The wrong blood comes in and it reacts to what is on the hemoglobin. It's reacting to these little oligomers of monosaccharides. Oligomers, so 4, 5, 6 saccharides together are going to tell you what blood type it is. All right, you get these antigens. All right, we'll get to the polysaccharides. I'll tell you what you can do. You've got a few minutes, so go back there and find an empty, fairly empty, none of them are empty, but a fairly empty kit, and tear these apart.
Yes.
Everyone put it in theirs in a different kit. And we're done with these molecules.
Dude, I've been trying to join the Visine from every time
And I will take attendance.
there's no more appointments.
All right, listen for your name. Rick, Jessica, she was here. Vanessa, Paola, Joshua, Dustin, Tiffany, Aaron, Javier, Juliana, Christy, Cassidy, Gabby, Alma, Brianna, Carol, Matthew, Alyssa, Elizabeth, Samantha, Cameron, yes, Ryan, Amanda, Stephen, and Alexis.
I could have ripped it apart, yeah. My
Alexis?
coffee's wearing off, so this is my last bit of energy here.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 21. We got the 4, 5, 6, 7, 8, 9.
This is my workout for the day.
21. We got it.
Put it in
Okay. You may be excused. Rip your molecule apart, and you may be excused.